Good day, everybody, and welcome to Module 3 for Bio 2, where we are going to begin talking about Chapter 2. We're going to start talking about chemistry and the chemistry of living things. And so, generally, in this class, a lot of the students typically have a harder time with Chapters 1, Chapters 2, and Chapters 3. Mainly because these are more of the foundational chapters and where we talk a lot about obviously chemistry, cells, the components, the organelles, those sorts of concepts, which are really important for understanding this and having a foundation in this is really important for understanding everything we're going to talk about after chapter 3. And after we get past chapter 3, we'll start talking about all of the organ systems, right? Which, again, chemistry and all of those components and ideas are going to be a very big role, or going to play a very big role in understanding those ideas. And so, if you're having, I guess all this is to say is, if you're having difficulty, understanding the first couple chapters, don't fret. The remaining chapters will be more of kind of probably in your wheelhouse, because a lot of you are most likely wanting to go into the health field. So you're more interested in, say, the human body and the kind of organ systems and the organs and basically how the human body works, and not really interested in learning about atoms and elements and chemical bonding and all of those other things. And so just keep that in mind as we go through the next couple chapters. Okay, so some of the key concepts that we are going to go over in chapter 2 are we're going to define matter, we're going to define energy, we're going to talk about what each of those are. We're going to mention the different chemical bonds that link atoms together to lead to the formation of molecules. We'll talk about water and its properties and why water is such an important component to life. We'll talk about how living organisms gain energy and use it to make the molecules and to put chemical bonds together and to break chemical bonds. We'll also finish up with this chapter talking about the 4 classes of organic molecules. So those are carbohydrates, proteins, amino acids, and nucleic acids. And understanding how those 4 carbon molecules or organic molecules are put together, what they're made up of, how they're important for the human body is really important to understanding how all of the other organ systems and other processes that happen in our body work, how they get energy, and all of those things. All right, so first, we're just going to kind of get some key definitions down. So chemistry. So chemistry basically is just the study of matter and energy. And the term matter just refers to anything that occupies space and has a mass attached to it. So it has this mass, right? And matter, so all matter is composed of elements. So you can have the simplest forms of matter, which are just single elements, or you can have forms of matter that are made up of 2 or more different elements. Now, energy basically is the power to do work. And so energy can be stored, or it can be released to use work or to complete work. And we'll talk a little bit more about that as we kind of go through this chapter. And then finally, elements. So elements, like I had mentioned in the matter, is the simplest form of matter. And elements cannot be broken down into any simpler component. And we have what's called the periodic table, which I'm sure a lot of you or all of you are familiar with or have at least seen. And the periodic table of elements basically lists all of the elements that exist, okay? So we're going to go over a couple of things on the periodic table. So we're going to spend a few minutes kind of discussing the periodic table. But what I want you to first look at is, say, each square or rectangle represents a single element. These elements have numbers in the top, which is referred to as the atomic number. It has a letter or a combination of letters, that is the element symbol, and then it has a integer number or decimal number on the bottom that is the atomic mass. So that number represents the atomic mass. So for example, this element here is hydrogen. So hydrogen is represented by the letter H always. It has an atomic number of 1 and an atomic mass of 1.008. Now, if we look at carbon, so I'm going to focus on carbon because we're going to talk a lot about carbon today and throughout the rest of the semester. Carbon is denoted by the element symbol C. It has an atomic number of 6, and it has an atomic mass of 12.01. So with carbon, or with any element, the atomic number basically tells you the number of protons and neutrons that are in the atom. So carbon has an atomic number of 6, so that means it has 6 protons, 6 neutrons, and 6 electrons. Okay, because that atom is neutral, it has to have the same number of protons as electrons. Right? So protons have a positive charge. Electrons have a negative charge. Okay? And neutrons are neutral. Okay? That's kind of where the name comes from. Now, with these elements, we can determine how many electrons are in the outer shell based off of knowing the number of electrons. Okay? So every element has orbital shells that kind of go around the nucleus. Okay? So the C is going to serve as the nucleus, and then this ring is an orbital shell. This ring is an orbital shell. Okay? Now I'm going to put the electrons on these orbital shells. So the first orbital shell can only hold 2 electrons. Right? Sorry, I want to just do them as X's because my notepad doesn't like me doing dots. Right? So if we put 2 electrons in the first orbital shell, and we know that the first orbital shell, right, only can hold 2. Okay? The second orbital shell can hold 8. The third can also hold 8. Okay? So if we know that carbon has 6 electrons and that 2 will fill up the first shell and then the remaining electrons will go to the next shell. So that means there's 4 electrons left. So that means there's 1, 2, 3, 4. And so in the second shell, if there's only 4 electrons, that means that second shell has space for 4 more electrons, okay, in order to be filled. Now, the reason why I'm going over this is because atoms like to be stable. They like to have filled outer electron shells. So this second shell is the outer electron shell. And so atoms of those elements like those shells to be filled and like them to be stable. Now, as we'll learn in a little bit, some ways that atoms can fill their outer electron shells is to either take electrons from other atoms or they can share electrons from adjacent atoms, right? And so what this means is that carbon can take up 4 more electrons, okay? And so carbon then has the potential to bind to 4 different atoms, right? And we actually see this fairly often in carbon-based molecules. So the simplest carbon molecule, right, is CH4, which is methane. And so you have the carbon electron, right, the 4 that's on the outer side, but then you also have the electron that's the hydrogen electron, and so they will share, right? That's denoted by the blue X. So now with these 4 hydrogen atoms sharing their electron, now this outer shell is filled with 8 electrons. And hydrogen, right? So if we draw hydrogen here, it only has 1 electron. So that first shell is not filled because it doesn't have 2 electrons. However, if it shares that electron with carbon, hydrogen all of a sudden has a filled outer shell as well. Right? So now it has 2. And then carbon will have 8. And so all of these atoms here, all 4 hydrogens and all 4 carbons, will have filled outer shells, so they will be stable. So that's really important because atoms will make bonds to try to fill those outer shells. Now, carbon is interesting because it has 4 electrons that are needed in order to make that outer shell be stable. So it would generally make bonds. But if things like hydrogen, which only has 1 electron, it can sometimes give that electron away. So for example, sodium only has 1 electron in its outer shell, and so it tends to give away an electron to chlorine, which has 7 electrons in its outer shell. And so sodium will give an electron to chlorine, and now chlorine's filled, and then sodium will be filled because it will lose an electron because it has 1 extra, and then it will have an outer shell that's filled. And the way that I know this, so the way that I know that sodium has 1 in its outer shell and chlorine has 7 is based off of its place in the periodic table. So put some numbers under here. Right. Each column, each element in this column has 1 electron in its outer shell. Each element in this column has 3 electrons in its outer shell. So 4 for carbon's column, 7 for this column with chlorine, fluorine, and then the last column has 8 in their outer shell, and so they're already filled, they're already stable. So these are called the noble gases. Right? So these gases already have filled outer electron shells, so they don't really make bonds too often because their shells are already filled. But all of these other elements will make bonds pretty regularly because they want to get their outer shells filled. Okay? And so I know that's kind of a lot that I just went over using the periodic table. So I've kind of broken this down in some note form. So we can kind of, you can go through it as you study in a little more broken down, simpler form. So remember, atoms consist of protons, neutrons, and electrons. Protons and neutrons are always at the center of the atom, so they make up the nucleus. Protons have a positive charge, they have mass. Neutrons have no charge, and they have mass. Electrons have a negative charge, and electrons have no discernible mass. So they have a tiny portion, but it's very, very tiny, so it doesn't really add anything. So there's no discernible mass to electrons. Okay? Now, the atomic mass of an atom, therefore, is based off of the amount of protons and neutrons that the atom has. So, for example, carbon has an atomic number of 6. So that means it has 6 protons and 6 neutrons. So 6 plus 6 is 12, which is the atomic mass. Right? So carbon has an atomic mass of 12. Notice, though, that the actual atomic mass of carbon is slightly higher. So it's 12.01. And we'll talk about why that's the case in a few minutes whenever we discuss isotopes. So just keep that in mind. All right, so here's a figure that just shows the form of the nucleus and the electron shell of 3 different elements. So we have hydrogen up top. So hydrogen has 1 proton, 1 electron. It actually has no neutrons. Oxygen, it has an atomic number of 8. So it has 8 protons, 8 neutrons, 8 electrons. So that means it has an atomic mass of 16, right? And so you have those protons and neutrons in the nucleus, and then the electrons are in the outer shell. And so notice you have 2 electrons on the first shell, and then you have 3, 4, 5, 6, 7, 8. So 6 electrons on the outer shell. So that means that the outer shell needs 2 more in order to be stable. So oxygen, as you know, binds with 2 hydrogens, right, to make water, H2O. And so it gets the 2 remaining electrons from those 2 hydrogen molecules. Sodium, so Na, has an atomic number of 11. So 11 protons, 11 neutrons, 11 electrons. So sodium has 1 electron in its outer shell. And as we'll learn, chlorine has 7 electrons in its outer shell. And so sodium can actually give up that electron and lose it, and then its second shell is filled, so then it will be stable. But what happens when sodium loses that electron is it becomes negative, it becomes positive because it has more protons than electrons. So if it loses an electron, it now has 10, but it keeps the same number of protons. And so you can just imagine, if you wrote out 4, 5, 6, 7, 8, 9, 10, and did 2, 3, 4, 5, 6, 7, 8, 9, right? And you did crossing out, right? All of them will cross out but 1, and so that means it has a positive charge. All right, so just a little more about atoms. Again, we've already talked about the atomic symbols, atomic numbers, and atomic mass. So we said that atomic mass is roughly equal to the number of protons and the number of neutrons. And the atoms are typically electrically neutral as long as the protons equal the number of electrons. Now, there are times when you can get differences in the atomic mass relative to what you would expect based off of the atomic number. And this happens whenever you have isotopes of an element. So all elements will always have the same number of protons. Right? So those number of protons will never differ. However, elements can have differing numbers of neutrons. If these numbers of neutrons are different, then that means they will have a different atomic mass. And so, for example, carbon has the atomic number of 6. So that means it has 6 protons and 6 neutrons. So that means its atomic mass is 12. Now, if you remember, the element, the periodic table said that its atomic mass of carbon is actually 12.001. So now the reason that carbon has an atomic mass of 12.001 is because of the isotopes. Okay, so we said that a normal atom of carbon is going to have 6 protons and 6 neutrons. Now, an isotope of carbon, right? So there are 2 common isotopes, carbon 13 and carbon 14. Now, these carbons differ from carbon 12 because carbon 13 has 6 protons and 7 neutrons, and carbon 14 has 6 protons and 8 neutrons. Okay, so the number of neutrons are different for the isotopes compared to the normal carbon atom. Now, these are much rarer, so these isotopes are much rarer in the environment than carbon 12, and so they push the average atomic weight up by a thousandth of a decimal place to 12.001, right? And so you can imagine if you have 100 atoms that are 12, 1 atom that's 13, and 1 atom that's 14, say, the average atomic mass is not going to be 12, it's just going to be slightly higher than 12. And so that's where that 12.001 comes from. And that's why you'll see on the periodic table all of the atomic masses are typically higher than what their atomic mass doubled is. So for example, sulfur, you would think it was 32, but it's actually 32.06 because isotopes exist that push it up a little higher. Now, isotopes can come in the form of unstable isotopes, and these isotopes give off radiation, so they basically shed off particles, and these unstable isotopes are known as radioisotopes. And some radioisotopes can be really useful in terms of scientific research or medical uses. And so, for example, carbon 14 is radioactive, and we use it a lot in science to date fossils. The diagnostic imaging, so things like X-rays, uses that radiation to take images of the inside of our bodies. Cancer treatment uses radiation to kill the cancer cells. And then we also can use that radiation for nuclear power plants and for power supply, and also use them for things like cardiac pacemakers. All right, so isotopes have a lot of different uses in our daily lives. Now, as I mentioned, most atoms are stable, meaning that all of the shells are filled, like we talked about earlier, and all electrons are typically paired with another electron. So basically, for example, if you have, let me just look at the periodic table to see what's a good round number. Let's just use oxygen, right? So let's say we have oxygen is 8, right? So you would have your 2 electrons in the outer shell or the inner shell. In the outer shell, you would have your other 2. So that's 4, 5, 6, right? So they are typically paired together, right? And how they kind of go around that orbital. Now, there are also free radicals that exist, and this is where an atom or a molecule has 1 or more unpaired electrons. When this happens, they're highly reactive. And those highly reactive free radicals can actually damage proteins and DNA in our bodies. So that can cause damage to cells. It can cause mutations in our DNA because it becomes damaged. It can cause proteins to not work correctly, which causes downstream issues, as we'll talk about, throughout the semester. And then it also can speed up cellular aging processes because of the damage that happens from those free radicals. All right. And so that's it for the first video with our introduction into chemistry. In our next video for this module, we're going to talk about energy. We're going to talk about the different types of energy, and we will also talk about chemical bonding and the different types of chemical bonds that exist. So we'll see you in the next video.